I hope everybody is still awake. But no worries, I will try to kind of make fun of stuff and then show you some practical things, and that's how we will probably spend the next 45 minutes. So let's see where we can take this. I'm Philipp. I think this is the 3rd year in a row I'm here. So, hi Java Day. And well, today I want to talk a bit about machine learning and well, what you can do in practice with that and what is all the hype about and what is kind of like not the idea of machine learning. So I work for Elastic, the company behind Elasticsearch, Logstash, Kibana, Beats. I'm part of our infrastructure team, and then I always say this is a Unix pipe. I piped it out into developer advocacy, so I try to speak a lot about the good stuff that we do. And I will generally talk about machine learning or AI in the beginning. And then, since I'm an ops person, I will use a use case that we have every now and then where you want to monitor things and see how that works out. So, these are our products, and you see we have some machine learning component in there as well, because nowadays every single company needs to have machine learning somewhere in the name, just for the buzzword. And well, we're doing the same, so let's see if it's just a buzzword or what you can do with that. So every now and then I hear people say like, oh, machine learning is going viral now. It's like the big thing and it's spreading everywhere. And maybe you have seen that was like some month ago or half a year ago, there was this bug on iOS where whenever you typed an I, it would autocorrect it to a different letter. And that was actually machine learning going viral because that was like the new predictive keyboard Apple introduced, and it basically learned what people were typing. And unfortunately, it learned somewhere that it would try to replace that I with some other letter. And that was kind of like going viral on the machine learning interface. And somebody put it very nicely. You didn't have that before, and it wasn't programmed, but it was learned by the machine, by the predictive keyboard, and then it only started to spread. So whenever people say like, oh, machine learning is going viral today, that is pretty much of what I think about, that this is the kind of viral that is spreading. And yeah, and oftentimes people are using very fancy things, or at least very fancy terms, and the only thing that they would have needed is a few if statements. And you can probably think of this like you're using a big digger, and then all you're using is like this little shovel down there. And that is oftentimes what people are doing when they say like, oh, we're using machine learning and we're doing something very fancy. In the end, it would be something very simple and limited that would kind of do the right thing for you already. Have you seen this? This is the Gartner hype cycle. I think this is the only thing that is true that Gartner is bringing out, because the rest is normally like just some estimation or guesstimation. But with machine learning or any other new hype topic, you can always see like you're getting up to this peak of inflated expectations, and then you think, well, this is the best thing since sliced bread, and it's solving all my problems and everybody's problems. And at some point you realize, well, it's not doing everything I wanted. And later on you kind of find the plateau of productivity or kind of the right use for things. And we'll see where we are with machine learning today, and we have gone through a few cycles already. So will it solve all your problems? Unfortunately, no, it's not, but it is still a very useful tool, and there are some use cases where machine learning absolutely makes sense, it makes your life easier, but it's not going to solve all your problems. So we'll talk about machine learning or AI in general. Then I pick one domain, some server logs that I want to learn on, and then I'll just have a data set and try to find some anomalies in them. That's the program for the next 40 minutes. So, machine learning. What is the difference between those? Like, you hear people throw around artificial intelligence, machine learning, deep learning, like, what even is the difference? Some people say, oh, it's all the same, I don't really care about it. Others are like, no, there's a very strong difference. I will stick to this, like, kind of classical approach, but I think this is very valid and good. So you can see machine learning is very old. It started AI is very old. It started somewhere in the 50s. And what's the idea? You solve something with a machine, and afterwards you just broaden it out. And machines just are as good as humans in general and learn as humans and can solve problems just like humans. And that was the initial AI wave. And then at some later point on, it didn't turn out that well, and then it kind of like another wave came with machine learning. So this was kind of like, oh, it's learning chess. And after machine learning or AI has learned chess, it can solve all the problems. Well, that didn't work out. Then we have another wave, which was, for example, classifying emails as spam or not spam. That is something you can do with machine learning very well. So you basically learn what is something, or you do some classification. And then we've more recently added deep learning. This is often you see that somebody is trying to figure out like which number have you written. Like it automatically learns like what a number looks like or what a cat picture is, for example, and it can then tell you, okay, there's a cat in your picture. And that is some of the newer applications. So let's take a look into each one of them and how they developed. So the first thing, or the first idea, was to have this human-like AI. So computers will be just like humans in a few years. That was the idea basically in the 50s and 60s. It didn't really turn out that well because in the 70s you had the so-called AI winter then, which was basically people figured out, well, you can solve something for one very specific domain or problem set very easily, but making it broad and just solve all the things for you is much harder. And then the AI winter was basically people said like, oh, this whole AI thing has failed, like it's not going to work. And this broad AI that it's human-like, people kind of gave up on that, and now people are more like into narrow AI. Narrow AI is basically saying for one specific task, a machine is as good as a human or better. That might be playing chess, or more recently, what you've seen with the game of Go, not the programming language, where Google was beating the best human player. This is one thing where for one specific task, machines are getting better than humans. Or for example, this one. I recently took that picture and uploaded it off the Golden Gate Bridge to Facebook. And Facebook also has some image recognition, and for some tasks they are pretty good. For example, they could automatically detect approximately what it is. I didn't tag that and say, oh, this is the Golden Gate Bridge, but I just uploaded the picture without further information. And it could still infer that, okay, this is probably an ocean, the sky, a bridge, cloud, outdoor, water, and nature. So this is pretty good, and it has learned a lot of stuff just from looking at the picture. So this is maybe not as good as a human yet, but this is getting pretty close to like figuring out what you have in a picture, for example. Or Zalando, which is like shipping clothing stuff, especially in the German-speaking region. They had lots of marketing people, and those marketing people were writing newsletters to people and saying, oh, you bought these previous articles, maybe you're interested in that. And they were curating a lot of that content by hand and writing marketing material by hand. But now they want to customize that further and want to give each one or single user kind of something that is particular to their account and their buying history. And they've basically kicked out these people and said like, well, machines can do that better now. They can predict what you probably want to buy, and they can even write the texts like, oh, I have like these things that belong together, and this season is coming up, and it can advertise better than humans for a lot of cases already. So they have started to cut down on jobs for that. However, sometimes machine learning is failing, or AI. So this is a very complicated German sentence, and it's basically, it's different term for economics. And if you were putting that into Google Translate, it took that kind of like, those are not all the same words, but basically what Google Translate would get out is the economics of economics, including economics, blah, blah, blah. By the way, this has been fixed now. I'm not sure if Google Translate has learned that on its own, or if somebody went into the rules and said like, okay, we need to fix this and make some exemptions for that. But this is no longer the case. So machine learning or AI has learned for translations, and if you're a translator, maybe today automated translations are not that great yet, but there's a good chance that in a few years from now, automated translations will be actually very good. So maybe you should make sure you have a job in a few more years if you're specialized in translations. And then there's always this thing when you talk to somebody and they say, I ask them like, what are you doing? And they say like, oh, I'm doing AI. And I'm thinking about something very fancy or academic. And then I ask further, what are you really doing? And then they're like, yeah, I'm building a chatbot. And I'm always like, yeah, the chatbot. I always think when people say I'm doing AI and chatbot, it's like the P is silent because most of them are mainly using an API and not really doing AI. So that's kind of the thing I have with a lot of chatbots. For example, I'm not sure if anybody is using chatbots or developing chatbots. I don't want to hurt anybody's feelings, but I've had some bad experiences. For example, this one here is pretty popular for weather forecasts. And this is a common example of things that can go wrong, because just because you're giving cute answers doesn't make you very intelligent, because here pretty much everything is failing. At first it doesn't really figure out where you are, and then it doesn't figure out when, and then it's just trying to speak French, and then it fell asleep, and just giving something that sounds cute but is not helping you in any way in a chatbot. And if I had just looked at a regular old interface and clicked a few buttons or entered like my location and would have seen the forecast for the next few days, this would have been much better and easier. So chatbots can be tricky. Or something else that you might experience every now and then, some chatbots are stateful and others are stateless. And the statelessness can be super fun. when you talk to them, and every single sentence is kind of its own problem set, and they don't remember any context or history. So you might get something like this. Bad about what? So generally what machine learning is doing is you have some data, you parse it, and you try to learn from it, and then make some determination or prediction out of that data. So basically it's a trained machine that you have. You can put it in a very academic sentence, though you will not get any venture capital for that. And nobody will want to be hired by you if you say, like, we are doing this. So this is pretty much the academic way to put what machine learning is. Basically, you have some experience, and then you try to learn from it. And you can make it sound very boring like this, or you can make it sound very fancy. And then people are always like, yeah, this whole machine learning thing is super new. Like, everything is new and has just been invented. And this is totally not true. Like, the basic algorithms for the stuff that we're using in machine learning have been around for decades, or at least quite some years. So these are some of the very common algorithms that you're using, and you can see a lot of these papers are older than me and probably a lot of you as well. So it's not really the cutting edge stuff, it's just implementing them in the right way and using them in the right way. That is kind of a novel approach, but it doesn't mean that people have just invented everything around machine learning in the last few years. That's totally not true. So generally what you want to do when you learn in machine learning is you have something like a regression. A regression would be you want to estimate or calculate a future value, for example, the temperature tomorrow, based on some model. Or you want to model the stock price for tomorrow. Another thing would be ranking. That would, for example, be in a search engine. So you see people are searching for something, and then you see which hits are liked by users or clicked on by users, and then you try to push up the hits that are good hits further. So your system is basically learning to rank search results in the right order. Another thing would be clustering. Clustering would be, it could be either binary, just saying yes or no to something, or it could be multiple groups. So for example, that grouping could be, I have a visitor on my website, and now I want to determine, is this a real visitor? Is this a search bot that is just crawling the website to index my site into a search engine? Or is it a denial of service attack that I probably want to block? And based on that classification, you can treat that traffic differently. For example, the regular user should be getting everything very quickly. A search bot that is just crawling your site can get responses a bit slower because, well, the search bot can wait. It's not a human waiting for you. And the denial of service attack you would probably want to block entirely. So this is something that you could do when you do clustering or classification of traffic. And yeah, this is what you might imagine that machine learning looks like. It's one big machine, even though it's very hard to read, and all the others are learning from that. That's not really the case. It's kind of slightly different in the background. Does anybody remember TAI? That was a few years ago. It was some bot by Microsoft. It should be a teenage girl, I think, and it should just chat with other people on Twitter. And it would learn from what people would tweet at the chatbot. And unfortunately, people just taught it the worst or talked in the worst way to the chatbot, and it learned all those bad things. So it became, within one day, the chatbot became racist, sexist, and all the bad stuff, basically. And then they had to shut it down. So one thing you always need to remember, stuff that you don't want your children to hear or do, you shouldn't also show them to machine learning, because machine learning is just like children, and they will learn that. That is something you also need to keep in mind. Otherwise, it will kind of go the wrong way. So when you do machine learning, and I always assume when somebody says, like, we are doing machine learning, they're probably doing the simplest thing that they could do, and that is the linear regression. Basically, you have these points, and you want to find this line, which is kind of has the closest, the least distance to all of these points. So it's kind of like in the center of them. And the more points you have, the better this red line will be, or the closer it will get to where you want to have it. So this is linear regression. You want to optimize for whatever data points you have. You want to get close to all of them. The more data you have, the better your machine learning will be. So whenever somebody says we're leveraging machine learning, which sounds very fancy, I would assume they're just doing linear regression, which is helpful, but it's not super fancy or complicated. So just because it sounds very like magic, it doesn't need to have to be. And then you can still classify machine learning in supervised and unsupervised machine learning. Supervised machine learning is basically you have some data, and you have labeled that data and know the outcome of that, or you have labeled outputs. So you know what should be learned or what should be the outcome. This is helpful if you have that labeled data. Oftentimes, unfortunately, you don't have labeled data. So then you would normally use unsupervised machine learning, where basically you have some data set, and your machine is learning based out of that data set and tries to discover some hidden relationship. However, finding relationships is also tricky, and just because of the statistics, sometimes can go wrong. I don't know if you know this XKCD comic, but I think this is like a very good illustration of what can go wrong. For example, somebody says like jelly beans are causing acne, and then you're calling in the scientists to check out, do jelly beans cause acne? And then they say, we tested that, and with a 95% certainty, it does not. And then they say like, oh, but one color might be causing that, not the others, just one color. And then you test that. And then you can see we're doing 20 experiments, and you can see all of them are negative, except for this one where the other one says, whoa. This is the one where here, jelly beans are causing acne. And then what the news will report is, well, the green jelly beans, which just happen to be green, they're causing acne. The problem is, if you do the 95% confidence interval, that basically means if you do it 20 times, there is a chance that one time will be kind of outside of that confidence interval. So while you have shown some correlation, it was purely accidental because of the statistics are just working that way. If you had a different confidence interval, you would have more misses or fewer misses depending on your model. But this is something, just because you have found some correlation, that doesn't mean it really is there or it is there in any meaningful way. And your machine learning cannot show you that. It just can find these statistical anomalies then. Okay, and then something that also comes up sometimes, it's reinforcement learning. Basically, you have a feedback loop, and whenever you add more data, it learns and optimizes over what parameter you're adding. So it's just continuously learning and improving basically what you have based on the data you feed it. And then there is deep learning. Basically, deep learning has this neural network where you have these neurons, you have some input parameters, and you have some weighted inputs, and then it has this probably deep network of neurons, and at the end it will plop out some value and calculate that for you. This has been made possible because you now have lots of data and lots of parallel computation, because it's generally very expensive to calculate, but it can yield some very interesting results. For example, something very simple might be you have two inputs. You have people who are doing a test, and you know how did they sleep the night before the test, and how many hours did they study. And this network, without explicitly kind of telling it, okay, this should be modeled like this, will figure out this network and will afterwards say, okay, based on these input parameters, your grade will be probably this. So it will automatically learn based on how much you studied and how much you slept, what your grades will be. Don't tell that to any students, because otherwise they might try to just sleep, which won't work. And kind of the most important thing for that entire thing is you need a lot of data. Otherwise, you will not be able to learn stuff. And for example, this is a very old picture from Facebook. And initially, they didn't have any image recognition features. But what they had was that you could tag somebody in a picture and say, oh, this is this person. And this has been an extremely valuable data set for Facebook since then, because they know this person now, you know the gender, you know the age, you probably know some other things about that person. And this is now a huge data set they have, and they could train and learn on how to classify future images. And that's, for example, why they can easily figure out like the gender of a person. That is pretty easy in comparison. But they could also say like, okay, age, probably where they're from, and probably even detect or like know, okay, this is this specific person, just because they have so much data. And the data is kind of like, there's this common saying that it's like the oil of the information age, is having the right data and just extracting that information from that. And yeah, once you have huge data, then you can do even more things, like Trump would call that. So, when do you call it machine learning? When do you call it AI? I really like this tweet. Depending on which context you're in, you will do different things. So when you want to raise money, it's AI, and when you want to hire somebody, then tell people you're doing machine learning. It's kind of like what people want to hear. Just call it like that. Okay, so let's do something practical in the last 25 minutes. What do we have? I want to determine some patterns in data, or I have some data, and I want to see what is going on in my data. So for example, you have some pattern of users to your website. And you could have a trend. For example, your website is growing in popularity, and then like you have a linear growth of users to your website. Or this could be linear, or it could be exponential. It could be positive or negative, but you have some trend for the visitors on your website, for example. You could have some cyclical trends or cycles, which would basically be on weekdays, in the morning, people come to your website, and they're growing more over the day, and in the evening, that the numbers drop off, and at night, you basically have no or very few visitors to your website. So you basically have like daily curve or peak for your visitors. You also could have some seasonal spike. That would be, for example, if you're selling things, and you have some important holiday coming up, people might be just buying more. For example, Amazon is doing, I don't know, 40% or so of their revenue around Christmas, and that would be just a seasonal spike that they know and need to account for in the future. What is kind of bad if you have machine learning, if you have some totally irregular pattern, because, well, since it's irregular, you cannot learn anything and you cannot really infer anything from that. So as long as you have some pattern in your data, your machine learning could learn from that, but if it's just irregular, you are out of luck. And then you can have anomalies, because once you have learned what is kind of normal in your data, you can detect these anomalies. And that could be a point anomaly. For example, if you get cash from an ATM machine, every time you're getting, I don't know, 200 Turkish lira, and someday you're getting 500 Turkish lira. That might be an anomaly. And then the system might try to figure out, why did you get a different amount today? Like, is this still okay, or is this a fraud? You could have some contextual anomalies. Like, it knows, like, okay, you're always getting money in this one place, or you cannot be in two places together. But once you try to get data within an hour in two very far points or far apart points, something might be wrong. So this is kind of the context is wrong for your data. Or you could have collective anomalies. For example, collective anomalies would be like, okay, people are getting money from the ATM, that is fine, but suddenly more people than normal would get money from the ATM. On the other hand, nobody is paying by card anymore. That might, for example, mean that the card system to pay at these POS points might be down, and that's why everybody is trying to get cash out of your machines. And that would be a collective anomaly. So kind of for one user, that is kind of the right behavior, but over all the users I have in my system, they're behaving in a weird fashion. And then you have so-called breakouts of your data. What you could have, for example, you have a shift. For example, you have your application, you have deployed it, and once you deploy a new version of your application, it suddenly increases your CPU usage by 20%. And that would be just after the deployment, it just jumps up. You could also have some ramp up. For example, you're having an ad campaign and more people are coming to your website. Then it's kind of like over some period of time, the users on your website are growing. That would also be possible. And you want to probably detect both of them. Or you want to say a mean shift might be an anomaly, and the ramp up is just like the normal pattern how people are coming to your website. And yeah. Anomaly detection is totally supervised or unsupervised machine learning. The problem is most of the time you don't have that labeled data. So very few companies I know have labeled data of like, oh, these are all the past events that we have, and this was a good behavior, and this was an outage, and this was expected or unexpected. Very few have that. Most have like some data of the past, but normally it's not labeled because that's what you need to do as a human. So unsupervised machine learning is very commonly used for those use cases. So examples of what would be an anomaly in an IT system could be you have spiking 500s because somebody deployed a bad version, and then you see, okay, suddenly we have more 500s than we had previously, something went wrong. Or you have some security events. Security events could be, for example, DNS exfiltration. You're trying to get data out of a protected network by domain subnames, subdomain names. That might be something that might spike up there. Or you have some rare error events that shouldn't really happen in your system. All of these could be anomalies where you know your system is behaving in one specific way generally, but today it's behaving differently. And you want to figure out what is this different thing. You could totally have a dashboard and kind of see how stuff changes over time. The problem is normally your data is often complex and it's moving very fast. And humans are not really made to stare at these graphs. And sometimes anomalies are very easy to miss. For example, here, this is an actual example of, these are visitors to our website. And there is an anomaly in there. So these are the unique remote IP addresses on our website. And at some point, we had a small outage on our website. So we have an anomaly here. Does anybody see the anomaly? Probably not, because it's very hard to see. So as we will see later on, the anomaly is this little dip there. But this is the anomaly. And as a human, it's just very hard to see that. And we always jokingly say that there are not enough interns in the world to stare at all these dashboards and graphs and learn them by heart. So you probably want to learn something. The other thing you could do is you could say, I have some static rules to tell me how does this stuff work. I don't need this fancy machine learning. I will just define the rules, what is normal in my system and what is not normal. The problem with that is, what even is normal if you have like this cycle in your data? And you need to define all these rules up front. You then have false positives and probably false negatives. And whenever your traffic patterns change, you need to adjust your rules. So for example, here, what would be the lower bound and what would be the upper bound of the thresholds for you? Like, yes, you could set a lower bound threshold down here and one above, but that is very, very coarse-grained. So if you have an outage in the middle of the day, you probably wouldn't recognize that for quite some time, even though you should. And on the weekends, you probably would need to define the rules for the weekend, because the weekday rules don't make much sense here. And you can totally see, okay, 5 days, these are the weekdays, and then there's the weekends. Pretty much, you see what is happening, but it's very hard to define a rule for these patterns here. Yeah. So we need something that is doing machine learning, or whatever machine learning is doing here. So machine learning is generally very CPU intensive, whereas the data you store normally will mostly need memory and disk. Machine learning is just like Slack, which is also using a lot of CPU and everything else. So you could totally build that yourself now. So for example, once you have the data, you could use TensorFlow, Keras, Scikit. There are loads of frameworks how you can build that machine learning yourself and do that. That is, if you know these toolkits and have a data scientist and somebody who wants to spend like a month or two or something like that to learn that. The other problem with building that yourself is normally you need to kind of load the data and have the data in the right format. You need to store it, and then you need to optimize your algorithm continuously. And what people often assume, kind of like erroneously, is that your data is clean. That is one of the most common problems that you have in your data sets, is that you have like some dirtiness in your data or some minor outliers that don't make a big difference for real use cases, but which are kind of messing up your entire model. And then people are always asking, okay, so now please tell me which is the fastest machine learning algorithm that is out there. And this is the answer I always give when somebody asks me, like, okay, tell me the fastest system. Because whenever some vendor is doing a benchmark and showing that, this is pretty much what they are doing. They are finding some use cases or some use case where their system, this is the squid, is much better than their competitors, which is the house cat. Because under this specific scenario, the house cat has drowned, whereas the squid is just solving the puzzle it should solve. So this is whenever you see some benchmarks by a vendor, assume that it's also this one, and don't trust any vendor benchmarks. So generally what you want to do with machine learning when you have any patterns is you want to figure out the baseline, or what is normal. So you want to calculate that model. So what you probably have, if you have unsupervised machine learning, you would have something like this. This black line here, this is kind of, let's say, these are the users on your website, or the traffic you have on your website, or whatever. So this is the actual data that you have. And then you have the upper bound, which is the red line, and the lower bound, which is the blue line, and you're trying to learn what is normal in your system. And it could look something like this. In the beginning, it's very coarse-grained, because, okay, your traffic is growing, you assume the lower bound is also growing, but then you see, okay, it's falling, so I'll back off again. And then after a few iterations, you start to figure out what is kind of like the right pattern and what do I expect here. And you can see after a few iterations on the right-hand side here, the lower bound and the upper bound are getting pretty close to my black line, what is the actual use case. And once you have learned that kind of well, you would see, like, if that black line crosses out either of the red line or of the blue line, then you would have an anomaly, and then you could say, like, hey, something is wrong with the system. You need to fix something here. That assumes you have a normal distribution of your data, and it's not doing anything weird, because, yeah, sometimes you have stupid data effects which don't work that well, and they will mess up any statistical models you have, unfortunately. So we'll always assume you have normally distributed data. Otherwise, well, you're kind of in tough luck. Okay, so what could this look like in a machine learning context? So this is an actual example. We'll see that in action later on. So you can see we have a few iterations here. For example, here it takes 3 iterations until the system has learned what is normal. And after that, it kind of knows what to expect, and it has the right curve going up and down. What it also does is a good model is online and it continuously learns and ages out all information and updates with new information. So for example, you can see here we have an anomaly and here we have a traffic drop. And you can see the following day, the system is very unsure, like here's something unexpected might happen. So it kind of widens and learned that something unusual might happen. Because it's not sure, like, okay, I think this was an anomaly, but the model is still updating for the future to say, like, maybe something changed in the model and I need to adjust now. But this will also be aged out again, because if the kind of the pattern stays very regular like this in the future, these little spikes here will be aged out and will disappear over time. So a good model will always update according to the latest data it has seen. And yeah, and it can totally tell, okay, there was an anomaly, and later on it will age out these little spikes. So you can see here the spike is still pretty pronounced, but here it's kind of like getting very small, and over time that spike is then totally disappearing. So then you could think about, do I want a single metric? This could be, for example, the visitors on your website or the traffic, or do you want to break that down further into smaller subgroups? For example, you could have multiple metrics based on some specific field, or for example, the HTTP return code of your messages. And you could just have different models. For example, here I've tried to model the same data by country. And you can see the data is behaving very differently. For example, I don't know, France was very active here, but probably there was a national holiday or a strike or whatever the French people are doing. And they didn't have that much traffic anymore, but afterwards it followed some pattern anymore. And here we've basically just split that out into different models, one for each country, to learn what is normal for each one of them, and then just find an anomaly for one specific region and not all of them. Okay, let's do something practical. I have a data set, so this is an Nginx access log, pretty normal, what you would expect. So I have collected information, and I have enriched that with some GeoIP information, so I know, for example, this was a request from India, and I have a very coarse-grained longitude and latitude, and we have then basically what we did. So for example, you can see somebody with that IP address and an unknown user agent got some 200 message back, and we put that in our log. So now we want to show that data. So let's switch over to here. So this is the data set. This is actually from our own website, so unfortunately I cannot give you the data. We have slightly anonymized that. But this was like in February 2017 until March 2017, so a bit over a month. These were the visitors to our website. Oops, that's not what I wanted. And you can see we had about close to 14.5 million visitors to our website in that range. And you can see each one of these entries looks something like this. It's just the data I've shown you before. For example, here we have somebody from North America downloaded something and got a 200 back. So that's all good and easy. We could also graph that out and just see, okay, this is what my dashboards look like. So these are where the requests are coming from. These are the return codes. You can see, okay, this looks like a weekday. This is probably the weekend. Here we have another weekday or weekdays. Here we have another weekend. You can see which pages were most requested or which resources, how much traffic you were serving, and user agent. So that's all easy. And then you could try to find out, like, what is happening to my system? Do I have any anomalies? For example, here I've made two dashboards. One is the unique counts of IP addresses. And once again, we have this anomaly here, and it's this one here. This is basically the anomaly, where we have this little drop in traffic here. So this is an anomaly, but it's very hard to see in a dashboard. And then I've also tried to model the sum of traffic that we had on our site, but I couldn't see any really good pattern here. And I also couldn't see much of a correlation between the visitors on our site and the traffic. Yeah, I mean, here this drop here might correlate with this one, but it's still very hard to see in our dashboard. So I've thrown our machine learning job on that, and it has calculated the model. And what this looks like for this one here, let's make this slightly larger. So you can see this is all the data that we have. And you can see after about 3 iterations, the system starts to learn stuff. So you can see we have these 3 iterations where it's very coarse-grained, and then we had these 2 peaks where it thought, okay, I have found the pattern. The problem was, after 3 days, weekdays, the weekend came. So it kind of like was put off by that a little, but you can see after 3 more iterations, it also knew the weekend. So here we have the 3rd weekend. Here it even knew the pattern about weekends. And it had, after 2 or so, it started to figure out like what weekdays look like. And then once it has the weekend pattern as well, then the model got pretty close. And here now you can see that anomaly pretty well. So let's kind of like zoom into that anomaly, or let's make it like this. So you can see here, there was an anomaly. That was at the end of February last year. Anybody remembers what was then? Was anybody affected by that here? Let's see. There was this one big S3 outage from Amazon. And unfortunately, our own website had a dependency on that. And people couldn't download our downloads and couldn't load some websites. And kind of the good or the bad thing is that the entire internet basically depends on S3 to do stuff. So for example, the dashboard with the status changes on AWS, they couldn't update that because that also depended on S3, which was down. So even their own dashboard couldn't be updated because everybody had dependencies on that S3. And then we shortly thought about, well, should we add another cloud provider or should we add another availability zone? But then in the end, we learned that since everything is down on the internet and kind of everything is on fire, nobody cares if they can download our software. So in the end, we didn't change anything because, well, we didn't have a single complaint, even though nobody could download our stuff for an hour, because everybody else was down as well, so nobody kind of complained. Okay, and the other thing you can do is, for example, I am interested in a multi-model now. The multi-model might look something like this. So what I've done here is I have taken the response codes of my web server and broken down the model in these response codes. And you can, for example, see here, we had in the 400s, we had an anomaly here. And if I click on that, you can see here, we had an anomaly here. This was basically somebody published a blog post and had a bad link in the blog post, and then we had more 404s on our website. And you can see that very easily. Here, when it's getting kind of very noisy, you can see, okay, everything was good, and then suddenly we had more and more and more 400s. That was when we're using some weird CMS system for our blog, and there was some change to the blog system, and that added a lot of 404s. And at first we were kind of like panicking where all the 404s coming from until we figured out, oh, it's the CMS system that is screwing up stuff. How do you actually find out what is causing an outage? And for that, one common approach is counterfactual reasoning. So basically what you're doing is you have an anomaly and you're taking out one specific group of traffic. For example, you take out a specific range of IP addresses, or you take out a specific country, or you take out specific response codes. And if the anomaly is then gone in your data, you know that this is causing the anomaly. For example, if one specific country is causing the anomaly and you take out the country from your data set, then the anomaly is gone and you know, okay, this is the thing that is actually causing my anomaly. And you can figure out here also what is causing the anomaly and where this is happening. For example, you could try to then correlate things. So we can say, okay, I have these remote IP addresses and the response codes. I try to combine those models, and for example, I can see here, they are both correlating. So here, I want to see what is going on. And you can then see you have the outage of our website, and right after the outage of our website, we had more 404s. So you assume these two are correlated, right? Looks pretty correlated. The problem was these two events were unrelated. We've seen that. And then you learn again that correlation and causation are not the same thing, because one was the outage of S3, which was okay, an external system, and the other thing was the change of our CMS system. And they were two unrelated events, but they were just happening at the same time. So it just looks like one was caused by the other. And well, you probably know this one about correlation and causation. Well, one asks, like, after taking the statistics class, did it help with thinking about correlation and causation that one causes the other? And the other one says, well, maybe. That's kind of like the right way to think about it. Or with correlation, you never know what is causing what. For example, there's this very interesting statistics that the cancer incidence in the US, I think, have spiked like sometimes in the 80s, and the cell phones came up in the 90s and 2000s. And what then people could argue is that cancer is causing cell phones. Because just from the data, it pretty much looks like that. But probably that is not the case, I assume. Yeah, so if you have some correlation in your data, if it's unrelated, it will mess up any model that you have. It will just not be able to fix that itself. So what you need to do in machine learning in general, if you have any metric that is noisy, you probably need to throw that out. We have tried it with all our data. Like sometimes you try to find something in the data, but it's too noisy and you're not finding anything. It's probably just not very good for machine learning, and then you just need to kick out the data. The final thing that you can do here is, and that is pretty fancy, is you can do future predictions, which look something like this. So I'm going to this single job of the unique visitors to our site, and what I'm interested in now is I want to forecast, for example, in, let's say, 14 days, how many visitors will I have on my site. So now my forecast is running, and you can see, let's make this a bit wider again. So you can see what is the number of visitors that we're expecting on our site. And you can also see the more or the further you go into the future, the broader or the more coarse-grained your model will get. For example, here, after 2 weeks, there's a lot of uncertainty in the model already. But it can be, for example, if you have like something around disk space or like resource usage, predictions for the future can be very helpful to figure out what will you need in the future, actually. And with that, we're nearly done. The other thing that we're working on right now is clustering, so we can detect what kind of user do you have on your website. Is that a real user, or is it a denial of service, or is it like a bot crawling your website? And then you can then react accordingly to your system. Okay, so to wrap up, we've talked about machine learning, artificial intelligence. I've just shown like some server logs and how you can try to learn things in them. And if you want to try that out and do something in practice now, there is one very nice paper which basically tells you like the best practices for machine learning and engineering. And they have some very interesting rules or like suggestions of what you should follow. The first one of them is, even if you don't have machine learning, don't be afraid. Just because it's a fancy buzzword, your product doesn't need to have it. It also helps if you have something that you understand and can interpret. So that will make debugging easier. If you have a lot of magic and fanciness, even if the model tells you, okay, this is what should happen in the future, you're probably having a hard time figuring out if this is true or not. And yeah, whatever you build today, you will probably need to iterate and change stuff in the future. And with that, that's it. I have some stickers up here. So if you want to have stickers afterwards, grab them. And yeah, I'm always taking a picture with you so I can prove to my colleagues that I've been working today. Because nobody knows where I am generally. Let's see, without too much light. Smile, everybody. Very nice.